So previously we looked at a little bit of the nature of the sound, and we focused a little bit more on the how the speed of sound changes based on temperature, environmental factors, and stuff like that. Well, today we're news. I'm going to show you another little aspect of sound that changes really frequently, happens all the time. And to help us out, we're going to actually use a little simulation thing. We'll do it over here. There we go. We got a little sound source there, a little red dot here. We'll just get going. Okay. So that little red dot there is giving off sound waves, nice and concentric circular sound waves. And we can change the frequency. If we make the frequency smaller, then the waves get bigger, and vice versa. If we make the frequency bigger, the waves are going to get smaller. That one's going to hypnotize me, so we'll go back to this one. Something like this, okay? Now, the other slider here is a velocity ratio type thing. And of course, this thing isn't moving. But what I'm going to do is I'm going to get to start moving. It sort of bobs to the left a little bit, and I'll get it moving. Now, while it's moving, it's also giving off sound waves. You can probably tell that when it's moving and giving off the sound waves, and we can pause it here a little bit, the sound waves aren't the same everywhere. You can see the waves are sort of being squished together in the front, and they're sort of stretched out a little in the back. Now, this should look familiar to you technically from grade 9 science when you guys did your astronomy unit and you guys looked at the motion of galaxies and stars. A lot of you guys probably recognize this. This is the Doppler Shift. And the Doppler Shift or Doppler effect is about how waves are changed based on something moving. And in grade 9 astronomy, you do a thing with the Doppler effect, red shift and blue shift of stars and galaxies to show that they're actually moving, and which led to like Hubble's law and showing the universe was expanding and the Big Bang Theory and that type of stuff. So we're going to look a little bit today at the Doppler shift and how that actually works and how we can find out some stuff about it. So let's get rid of this for now. We're going to move that out of the way. And let's get going here. So we are going to look a little bit at the Doppler shift. And the Doppler shift occurs when you have some kind of moving wave source. It doesn't have to be sound. It could be any kind of wave source you want, but you have a moving wave source. And because you have a moving wave source, both of the wavelength and the frequency will actually change, and depending on where you are and your positioning and that type of stuff, okay? Now, if I bring in the simulation again, especially, we'll give me blah, blah, something like this. Especially if I go faster, so maybe like 0.8 or something like that, you can see there's a huge change. So the faster you go, the bigger the change is going to be, both in front and behind. Technically, right beside it, there's like pretty much no change. It's all before and after. And there's still circles. I mean, there's still circles. They're just not concentric anymore. So we're really focused more on what's happening in front and what is happening behind. And the faster you go, the bigger the difference is actually going to be. Okay, so if we go back to something slower, still occurs, just not quite as obvious. Okay. So I'm going to draw a very similar diagram here. I'm going to draw them a little, those are red in a little simulation. So a little red source. And let's say it's moving this way. And when it's moving towards the right, we've got waves in the front. And the waves in the front, if you remember, the waves in the front sort of were getting squished together. So the wavelength is going down, so the frequency actually will increase. And behind it, that's where they were sort of stretched out. And behind it, our wavelength actually goes up, so the frequency is going to go down. Now, of course, frequency and wavelength are connected. You got the wave formula V is equal to F lambda, and you can sort of see why as one goes up, the other one goes down, vice versa. But the speed stays the same. So in order to have the same speed, whatever the wavelength goes up or down by, the frequency will sort of do the exact opposite. Okay, that's basically how it works. Now, how much do we actually have changed? Well, let's bring the simulation again. It's going to sort of show you again. If we look at that velocity thing, it's not in meters per second or kilometers per hour. It's a velocity ratio. Well, a velocity ratio of what? Like it's going 0.4 what? Well, if I actually crank this up to an even 1 and do it now, you can sort of see what it's actually a ratio of. It's actually traveling and meeting up and staying with the sound. The actual source is traveling at the exact same speed the sound is. And that's what the velocity ratio is. It's actually traveling the same speed as sound. So if it goes down maybe to 0.5, okay, How fast is it going? Well, it's going 0.5 the speed of sound. So this thing would be going at half the speed of the sound, and that's why it's 0.5. And how much the frequency and the wavelengths change is directly connected to this. The frequency and the wavelength will change by the exact same ratio that the velocity ratio is. Okay, so it's actually a really simple idea. So let's get rid of that. So if we go back to our stuff here, let's say this thing is moving at 20% the speed of sound. So maybe the thing is traveling at 20% the speed of sound. Well, if this thing is traveling at 20% the speed of sound, the wavelengths and frequencies in front and behind will both change by 20%. Now in front, the wavelength got smaller, so the frequency went higher. So the frequency actually goes up by 20%. So in front, it would have a 20% higher frequency. And behind it, the frequency actually goes down by 20%. So it doesn't matter before after, but it's all the same percentages. And that's how you know how much change you are going to have with the Doppler effect. It's all the percentage of the speed of sound you're actually traveling. Now to show you how to actually incorporate and calculate stuff with this, we're actually going to go shopping for a second. Suppose you found a sweet physics mug here, and we'll put a little price tag on there. So your little price tag on there, and let's say it is $15. Well, you're not going to pay $15 because, of course, there's tax when you go shopping. Now, let's say maybe let's just make this up. Maybe there's 7% tax. And then to get the cost, you guys, I mean, it's basic math, you do the 15 times 1.07, and that would give you your overall cost. Well, let's sort of expand on this a little bit and sort of show where this actually comes from, because how that is actually calculated is the exact same way the Doppler shift is actually calculated, okay? It's the same idea. So if I bring that over here, the cost of my mug is going to be equal to, let's just say the price, the whatever's on the price tag, okay? And you're going to multiply that by 1.07. So where's that 1.07 come from? Well, I'm just going to put P for price. The 1.07 is actually a combination of two things. First of all, you multiply by 1 to include the original price. But then what you do is you add 7%. But 7% is actually 7 out of 100. So you're actually adding 7 out of 100. And what you're doing is you're adding tax, and tax is 7 cents per dollar, or 7 cents out of 100 cents. And that's where the calculation actually comes from. So the cost is going to be equal to the price, and then you multiply it by 1 to include the original price, plus then the ratio of how many cents you are using for tax out of the total number of cents. Well, the frequency calculation is the exact same idea. There's no difference between the two. So we just modify this exact same expression with frequency type stuff. It's the exact same idea. So to find the new, I'll change my color here. To get the new frequency, okay, to get the new frequency or total frequency that you would get, you actually are going to do the same type of calculation. You are going to start with the original frequency, which is like the price. You'll start with the original frequency, and then what do? Well, you're going to multiply by 1 to include it, and then you are also going to, you also incorporate the percentage higher or lower of the speed of sound you're traveling. The same way, you know, it's 7 cents out of 100 cents per dollar, we want to incorporate the ratio of the speeds. Remember, if we bring the simulation again, it was the speed ratio. So, you know, like you're traveling at 0.5 the speed of sound, or half the speed of sound. So what you want to do is include the ratio of the speeds. So instead of a money ratio or cents ratio, we're going to include a speed ratio. And that's how we can calculate the new frequency that you're going to hear. Now, of course, the same way with shopping. Sometimes you use percentages, like with tax, to make things higher. Sometimes you would use sale prices, because, you know, things go on sale, and then if maybe it's 25% off or something like that, well, then you do, you know, the 15, and then you do 1 minus, or 25% off, 25 out of 100 to get the sale price. Well, the same thing with this type of thing. Sometimes you'll see a plus, sometimes you'll see a minus, because sometimes the frequency get higher, sometimes the frequency can get lower depending on the situation. So what you'll often see is frequency primed, which means a new frequency or altered, is going to be equal to the frequency 1 plus or minus the speed ratio, or the speed divided by the speed of sound. And that's how you can calculate the Doppler shift for any situation. Again, almost identical to just calculating the cost of something that you buy. Okay. Okay, so let's practice this, because it looks kind of fancy schmancy and hard, but it isn't. And once you actually see how it works, it's not actually that bad. Okay, so let's bring in a scenario here. Oh, here we go. That's what I wanted right there. And let's practice a little bit and sort of show you how this works. So we got a couple of guys here going for ice cream. All right, so of course we've got the ice cream trucks, and of course ice cream trucks have little bells and stuff on them. And let's say a little bell or whatever is giving off 5,800 hertz chiming type sound. We got one guy here, he's already got his ice cream, and he's taken off. And let's say he's running away at 3.6 meters per second. And then we got that guy with all of his fat stacks. He's got all his money here to buy loads of ice cream, probably for his physics teacher. And let's say he's running towards the truck at 4.5 meters per second, something like that. So let's see if we can find out what frequencies these guys actually hear, because we've got motion, and it's not actually the source of the motion, it's actually a relative motion between things. And let's see what kind of frequencies these guys are going to actually hear. All right, now I'm going to start with the guy on the left, a guy with a little sweet chocolate ice cream action going on. So we're going to start with this guy over here. And we're going to find out what frequency he is hearing. So I'm going to start with my expression. Frequency primed is equal to frequency 1. I'm going to leave the middle out for now. V over Vs. Now, sometimes it's plus, sometimes it's minus. Now, which one is it? Well, let's see. He's running away from the ice cream truck. He is getting further away. So since he's separating, sort of expanding things out, the waves should get bigger, so the frequency should get smaller. So since he's running away, I am going to want to minus them, because he should hear a lower frequency because they're separating. So I just got to put in my values. My original frequency is 5,800. And it's 1 minus, let's see, he's running at 3.6. And the speed of sound, give or take, around 340. So divide out the fraction, do 1 minus that, and then multiply it by the 5,800. And we get a frequency of about 5,739 hertz. Now notice that it's not actually the truck that's moving, it's the guy that's actually moving. And that's because this V right there, this is the relative V between the two. It doesn't have to be just the source that's moving. As long as the source and the receiver are, one of them is moving or they're moving relative to each other, it makes a difference. You get a Doppler shift out of it. Okay, and of course, it doesn't matter if you're going farther away or close together, it's all about relative speed. Okay, so now I can do the exact same thing for Mr. Fat Stacks over there with all of his money. So let's do the same thing for him. Frequency primed is going to be equal to the frequency 1 V over Vs. Now add or subtract. Well, this time he's getting closer. So since he's getting closer, he should hear a higher frequency. So in this case, I will want to add the two together. So original frequency, 5,800. 1 plus 4.5 over 340. Multiply them or divide out the ratio, add the 1 to it, multiply it by the 5,800. And hopefully we'll get about 5,877 hertz. So the two frequencies they hear are actually relatively similar, but humans would actually be able to tell the difference between the two. And you can definitely hear Doppler shift all the time with like police cars, fire trucks, ambulances, especially when they're driving fast past you and they're coming towards you. It's a much higher pitch because they are compressing the waves when they're coming towards you. And then as soon as they get past you, it is a way lower tone, okay? Because now the waves are expanding out because it's going away from you. So, and things don't even actually have to go that fast. Even just a car going down a residential street, just with the sound of the tires and the car, just the car noise. If you actually pay attention, you can actually notice it. Okay, so that's how to do Doppler shift. And again, the formula looks really fancy, but once you actually break it down, it's actually relatively simple and straightforward. And again, you know, it's just like calculating like a shopping type thing. Okay, you just got to be careful. We're getting closer together, farther apart. Closer together, you want to add. Farther apart, you want to subtract.